Hi and welcome to Algorithms Made Easy. In this video, we are going to see the concept of longest increasing subsequence in detail along with this question that is there on the Leetcode. So let's not waste the time and dive into the question. Given an integer array nums, return the length of the longest strictly increasing subsequence. Now, we are going to see the question in detail and we are also going to first understand the basics of what a subsequence is and how we can build up through the question to get to the optimized solution from the basic brute force solution in this video. So stay tuned and watch the video till the end. Let's start with asking the question of what is a subsequence. Now, a subsequence is a part of a sequence where the elements are in the same order as the original sequence, but some elements may have been skipped. What it means is that a subsequence is a subset of the original sequence where the elements may have been skipped while maintaining the original array sequence. So now let's take one of the examples that was given to us and see what are the subsequences that we can form from that particular array. So here is the first example that is mentioned in the question. And now let's form the subsequences. If we start from 10 and try to form an increasing subsequence of the array, if we start from 10 and include this element in our subsequence, the only element we can include after 10 is the number which is higher than 10. And in this array, the number that is higher than 10 is either 101 or 18. Now, if we include 101, can we include 18? No, because after 101 is included, we need something that is higher than 101. So, we will have a choice to choose between 10, 101 and 10, 18. Let's see some other sequences as well. If we start from 9, again there is the same scenario that the number higher than 9 is 101 and number higher than 9 is 18. So same, these two sequences can be formed. Now when we start with 2, we have a lot of options. We start with 2, we can include 5 because yes, 5 is greater than 2. Now when we have included 5, we cannot include 3, but we can include 7. And after 7, we can include 101 or we can include 18. So here are two examples of the many subsequences that we can form from starting with 2. Now, let's see what happens when we start with 3. When we start with 3, the subsequence that we can form is with 3, 7, 101 or 3, 7, 18. Similarly, we can form various other subsequences as well. These are just the sample subsequences. Now, amongst these, the subsequence which is the longest is this one or this one. Both are of length 4. And this is the highest or the longest we can go while making the increasing subsequence. So we can output 4 in this particular scenario. Once we have seen this, let's just go one step deeper and see what is it that we are doing while selecting these elements that are going into the subsequence. So let's take a smaller example and we'll start with a blank subsequence. So this is a blank subsequence that we are going to form, and while iterating at each step we are going to have two options, whether we can select that particular element in our resultant subsequence or we can skip it from our resultant subsequence. So that's what we are going to do. So let's start. First element is 4. Initially our subsequence was blank. So we have an option of either including 4 or skipping 4. So when we do both these things, our subsequences are as shown. So we have two resultant subsequences option that we can have. Now, let's go to 2. Again at this 2, we will be doing the same. That is either select the element or skip the element. Now in what subsequences are we going to do this? We are going to do it in the resultant subsequences that we have got from the previous step. So in this 4, and in this blank one, we are going to have 2 more bifurcations. And if we go ahead with this, we have 4, 2, 4, 2 and a blank one. Now, pay attention to this particular one. 4, 2. Does that satisfy the condition that our question is telling us? No, because it is not in an increasing order. 2 which comes after 4 makes it a decreasing subsequence, and that is not what we want. So do you think that adding or iterating over any other element while we have this particular subsequence is going to make any sense? No. So what we are going to do is we are going to stop iterations after this particular one, and we are going to take that this is the valid subsequence that we have till this particular point. So now when we are having 3 with us, we are going to again make the decision of whether we are going to select that element or we are going to skip it. So let's do that. And these are the resultant ones. Again, when you see this 4,3 is not an increasing order. So we are going to stop iterating over here for this particular line. And we have these elements which are still valid as a increasing subsequence. So we'll move ahead with these in our further iterations. So we go to 1 and we again make the decision of either we are going to select it or skip it. So with 4, when we do it, we get 4,1 or this 4. Same with 2, 3. Same with 2. Same with this one and last one as well. Over here, if you see, adding this one has made our subsequence not adhere to the increasing subsequence condition. So all these subsequences are of no use, and we can just stop iterating for these ones here itself. Remaining with us are these ones which are still in the increasing order or the valid subsequences. So again, when we go further and try to add this 5, we are going to have 2 options of either selecting it or skipping it. And when we do so, we are going to get these subsequences. And now, if you see that 5 was the largest element, so it can be added to all the subsequences that were there. And this becomes our final tree of mostly all the subsequences that were possible. The only places where we have not gone further is the ones where we have got invalid subsequences. And the longest one is this 2, 3, 5. So the longest subsequence length in this particular thing is 2, 3, 5. Now one thing to note over here is how many subsequences are we forming? We are having 2 options, select and skip. And this thing we are doing for n number of elements. So the total number of subsequences that you will be getting are 2 raised to n. Secondly, the question is how we can solve this particular thing using the coding approach. So one of the ways is recursion, because this looks like a recursion tree. So you start with a blank one and you go recursively till the end and return the highest number that you can get. So if you are taking a recursion, what you are going to do is you are going to iterate for each element, and for each element you are having 2 options, select or skip. With this, what you're going to do is you're going to check whether the newly added element is going to give you an increasing subsequence or not. And thirdly, you are going to keep a track of longest length subsequence that you have found, because that's the thing that you want to output. So these are the 3 things that we are going to do in the recursive approach. But what is the time complexity over here? The time complexity is 2 raised to n, because we are going to have 2 raised to n paths while we are selecting or skipping a particular element. Now, is it a good option to go with this 2 raised to n approach? No, because it is an exponential time complexity. And if you do this in an interview, the interviewer will tell you to decrease the time complexity and he or she will not accept this particular solution. So how do you optimize it? Let's go back to the graph. So over here you can see that there are a lot of things that are repeated. For example, this 4 is repeated. This 2, 3 is repeated. So why do you want to calculate the result for each and everything again and again? You can just use the result that you have got earlier rather than going forward with the recursion approach again. So that will reduce your time complexity. Now what is this thing called? This thing is nothing but memoization. So while you are doing memoization, while you are trying to save that particular answer or the intermediate result, you will also need an extra memory. So that adds one more step into your process, which is nothing but keeping track of the current subsequence answer that you have found so that you can reuse it later. So let's go ahead and first write out the code for the recursive approach, and then we'll try to write or make some tweaks to make it a memoized approach. Before moving to the code, let's again see what we are going to do in the code. So let's go to the graph again and see what is it that we are recursively trying to achieve. So when we are at this particular position and we are going to go to this particular positions, what we have with us is the last or the previous element that we added, and we are either trying to add the new element or skip it. So what we are going to need is what was the previous element that was added. For example, if you go over here, the previous element that was added was 2, and now you are trying to insert 1. So we need a track of that. So we are going to have these two things in our recursive calls. And now let's go and code it out. So what we are going to do is we are going to call a recursive function. So let's take the name of that function as lis, and we are going to take the nums array that is there with us, and we are going to take a current element which is 0th index, and we are going to take the previous element that was added, which is -1, because for the first iteration we are not going to have any previous element, so we'll denote it with -1, and this is something that we are going to just return. Before returning this, let's take a base case that if my length of nums is already 1, we just return 1 and do not do anything. Now before writing this lis question, let's take a base case where the length of the nums array is 1. So in that case we are not going to even go to this lis function. We can simply return the length of the array. So we are just going to do that. If that is less than equal to 1, just return nums.length. So 0 or 1 can be returned from here. And now we are going to write this function, which is lis, and we have the input nums with us, we have the current index with us, and we have the previous index with us. In this particular thing, what we are going to do is calculate what happens if we skip the current index and calculate what happens if we do not skip the current index. So let's say if this is the skip one. So the skip one, we'll have a call to lis of nums. We'll go to the next index. So we'll take current index plus 1. And since we have not taken the current index into consideration, the previous index still remains the same. So over here we can simply write previous index. And we also need a select one as well. So let's just keep it -1 for now. And we are going to only select the index if the current number is greater than the one that was found on the previous index that we have chosen. So if nums of current index is greater than nums of previous index, then only we are going to update this select one. And this is nothing but 1 plus the result. So that is lis of nums current index plus 1, comma, the previous index now becomes the current index, because this is the one that we have chosen for the next iteration. That's it. Now over here initially we have also taken -1. So what we are going to do is we are going to add a base condition for this as well, that if previous index is equal to -1, then also I am eligible to select that index. So that's it. Now what is the exit condition? Exit condition would be when my current index has reached the end of the array, because after that there are no other elements that I can process. So if current index is equal to nums.length, simply return 0. Finally, the actual return statement will be the maximum of skipping or selecting that value. So maximum of skip and select. So that's all for the recursive approach. Let's run this, and it is giving the perfect result for all the examples that we have. But if we submit this particular solution, this should give us a TLE, and that's what we have got. because it will take a exponential time. So now what we are going to do is we are going to memorize this answer. To memorize, we are going to take a DP array. So let's just take a DP array, and before that we'll store this one in a variable so that we can use it easily. Now what is this DP array going to contain? So DP array would be a two-dimensional array, and what is going to be the length of this DP array? The length of this DP array will be n for the n elements, and since we initially take previous as -1, we'll accommodate that as well in our array by taking the length or the columns as this, so that the previous of this -1 is also there with us. And now we'll fill this particular array with -1 so that this condition is satisfied that we have written over here. So DP, once we have this, we are also going to pass this DP array with us. So it will be passed in here. And what changes are we going to make in this particular one? This base or the return condition remains the same. One condition that we are going to add is take into consideration whether the result was already formed or not. So for that we are going to check this DP. So we will check for current index and previous index +1, because -1 is not going to be there with us, so we'll do a +1 for that to accommodate it. If this is not equal to -1, which means that it has been calculated, you just return that value. So return this. While you return this, everything over here will be skipped. And if it is not there, we'll calculate it with the basic things that we have and just pass DP with this. So over here we pass DP, and in this call as well we are going to pass DP, and at the end we are going to save the result in DP. So this becomes this, and we can simply return this instead of doing the math.max. That's all. What we did over here is we just took this DP array and we just wrote a condition that if the result is already there, use it, and we saved the result. Let's see, there is one mistake that we have done. This is going to be an integer array, not just int. Let's run this. It's giving a perfect result, and let's try to submit this memoized approach, and it got submitted. Now what is the time complexity for this particular approach? The time complexity over here gets reduced to O of n square, and the space complexity has increased from recursion stack space of O of n to O of n square for this DP array. Now we'll see one more step down the line to reduce the space complexity from this to something which is lower than this. So let's go ahead and see that approach. So this is where we stopped, where we tried to memorize the recursive stack and reduce the time complexity, but doing that with the recursive approach of this one gave a space complexity of O of n square because we took a 2D array. Can we remove that 2D array and go a little bit down? So to do that, we are going to use dynamic programming. The concept behind dynamic programming is using the pre-calculated values to calculate the current value. So over here we are going to just take a 1D array instead of a 2D array and try to see if we can solve it with this particular array itself. Now what does this array depict? This array depicts that including this particular element, what is the longest length of subsequence that I can get. So initially, if you include any of the element in a subsequence, the smallest one that you can get is of length 1. So what we can go and do is we can just go and fill the entire array with 1, because that's anyhow we are going to get. So let's do that. So this got filled with 1. Now let's see what happens when we consider this particular 0.5. Now when I'm considering this, what I need to know is what was the previous element that I have selected. Let's say I selected this 10. Can I select 5? No, because 10, 5 is not an increasing order subsequence, but it goes into the decreasing order. So I cannot do that. So now what I can do is skip this, go to 9. If I go to 9 and see whether if I select this element as the last element, what is the longest length subsequence I can get. But selecting this 9,5 is also not possible because this is not an increasing order subsequence. So we go to 2. Now, if this was the last selected element, can I add 5 to this and make an increasing subsequence? Yes. Now, what would be the length of this subsequence? The length of the subsequence would be the length that I have found at this particular point plus 1. So this is what we represent in this particular array. So if I say what is the value that is filled in this array at this particular index represent, so this represents the largest or the longest length of an increasing subsequence when I consider this element to be a part of that subsequence. Over here in this case it will be the increasing subsequence length that was there till 2 plus 1. So that will come up to be 2. Now that we know the basic idea behind what is the use of this one-dimensional DP array and what this is going to hold, let's take an example and do a dry run over it. So let's take the same example. We'll start with the current element of 9 and say that the last selected element is 10. First question is it feasible to consider this element when I am selecting 9? So this element should have been smaller than 9 and that is when I could have considered it. But since over here this is not the case, I am going to skip it and move ahead. So my iteration now went ahead and now I am going to the next element 2 and seeing whether I can include this 10 into it. Is it feasible? 10, 2? No, not again. So what I'm going to do is I'm going to shift this pointer over here because I still have elements that I can consider. So 9. Can I consider this? Since 9 is greater than 2, I cannot. So the only elements till 2 that I could have considered were 10 and 9, which are over. So now I need to iterate to the next element. Now the iteration for this particular 2 is over because till this 2 there are only 2 elements that we could have considered. So I am going to shift this pointer to 5 and while I am taking 5 I again start from the first element and see whether I can get a longest subsequence considering this 5 with this combination. So 10 and 5 not possible, so we move ahead. 9 and 5 again not possible, so you move ahead. Now this is possible because 2 is smaller than 5 and if I am considering this 5 to be a part of subsequence, this 2 can also be a part of this subsequence. So any subsequence that was formed with 2 being the last element would be a part of the subsequence with 5 as well. So what is going to be the result over here? Result is going to be the maximum of the current value that was there, or you can add 1 into the last selected element's value because I am going to select the subsequence that was formed in this particular position with 2 being or this element being the last element in that subsequence, plus I am going to add this 5 to that subsequence, so my length goes 1 plus this subsequence. So that is the result. So moving ahead, we are going to go to 3. With this 3, we are also going to go from 10 till 9, then 2 and 5. So 10 and 9 are not going to adhere to the increasing part. So 2 comes in picture. Now with 2, I can make this subsequence and that will be the subsequence that I found at 2 plus 1. So that can give me the answer of 2. Again, there is 5 that I can take. So if I go to 5 and see what is the longest subsequence I can get, I'll first check whether 5, 3 is a valid one. That is not there. So I cannot take this 5. So this 2 and 3 was the one that we could accommodate. Now let's move to 7. Again with 7, 10 and 9 are of no use. For 2 we can do. And for 2 the answer would be this 1 plus adding this 7. So 1 plus 1, which is 2. Moving ahead, if we take 5 into consideration, we can again form a subsequence, which is in the increasing order. So the answer over here would be the subsequence that I found with last element being 5 plus 1, or the value that is there in this particular position. So the maximum of this would be either 2 or 2 plus 1, which is 3. So we can update this value. If I take 3 into consideration, again there is going to be the same result, because 3 and 7 is also possible, and the length of subsequence that I got for this 3 was 2. So 2 plus 1, which is 3. Now let's go to 101. For 101, we can pretty much cover all the elements, because all the elements before that are smaller than 101. So starting with 10, we can consider this 10. So it will give 1 plus 1, that is 2. If we go to 9, we can again consider that. That will also give 1 plus 1, that is 2. If we take 2 into consideration, again it will give this 1 plus 1 for the 101, which is 2. If we take 5, it will give 2 plus 1, which is 3. If we go to 3, it will give 2 plus 1, which is 3. Now let's go to 7. 7 already has formed a subsequence of 3 elements in it. So if I consider this particular as the previously ending element and add 101 to it, it will give me a subsequence of length 3 plus 1, which is 4. Let's move to 18. Again with 18, same scenario is going to be there. If I come to 7, I'll get 3 plus 1, which is 4. And if I go to 101, 101,18 is not possible. So this is the last previous index that we could consider if we are taking 18 into consideration. The maximum that we have got in this array is 4, which is the answer. This was the dry run for the dynamic programming approach, where we are going to take a 1D array and solve this for each element. Now let's go and code this approach out and see how that looks. So this was the previous solution that we had. Now what we are going to do is we are going to take a 1D array instead of 2D array, which is going to be of length n, and we are going to fill this with 1 instead of filling this with -1. So just remove the for loop, because this is a 1D array. Fill it with 1 and then iterate over it. This lis function is not needed. Instead of this, we are going to take a max element which is initially 0, or we can take this as 1 as well, and at the end return max length. In between this, we are going to do what we were doing in the dry run. So for starting with the first element, and inside we are taking another for loop which is going till I. So this is the loop that we are going to take. Inside this, we first check whether we can add this element. So this j is the previous last element, and I'll check whether nums of I is greater than nums of j. That means we can add this particular element, and in that case we are going to fill our dp array for I, which is going to be maximum of I or 1 plus dp of j. Finally, for each element we are going to update this max length. Max length will be max length or dp of. That's it. Let's run this, and this is dp, not rows. Let's run this again. So it is giving a perfect result. Let's submit this, and it got submitted. So now what is the time complexity over here? Since this is a nested for loop, it is going from 1 to n and 1 to n maximum, so that becomes n square, and the space over here, if you can see, it becomes O of n. So this is a slightly optimized version from what we were doing in the memoization. What we did till now was we started from the brute force approach, went on to the memoized approach, and then went into the DP approach and reduced the time complexity from 2 raised to n square. while we reduce the space complexity to O of n. Now, can we do a little better from what we have done till now? Yes. But since this is a very long video and that is a little trickier approach, we will dedicate another video for that particular approach, which is nothing but a binary search that will take your time complexity to O of n log n, which is pretty exciting. So just keep watching the space of our channel because we'll be doing a complete detailed explanation on that particular approach in the coming days, and I am sure that you are going to like it and that is going to be very beneficial for your interviews. So please do keep watching, like the video, subscribe to the channel and click the bell icon so that you get the updates whenever we post any video on our YouTube channel. See you next time. Till then, keep coding, keep learning.